Alrighty guys, so this correlates with your reading guide online. I want to give you the brief of acids, bases, and just as a quick review for you because I don't think we need to spend time in class on it. Most of this is review. I'm going to do one new thing with mixtures that will allow you to calculate the pH of something that is not simply just an acid or just a base. Alright, so you know these definitions, acids and base definitions, so they come in three different ways: Arrhenius acids and bases, Bronsted-Lowry acids and bases, and Lewis acids and bases. So they all talk about different parts of the compound and what it does and how it reacts in a certain substance. Arrhenius acid is how it reacts in aqueous solution. Whenever you are talking about aqueous solution, we're talking about water. So what does acid do in water? It donates NH plus to water, H2O, to make the hydronium ion. What does a base do in water? It's just going to create the formation of OH minus ions or hydroxide ions. Bronsted-Lowry, how to remember this? Bronsted-Lowry acids are bad acids. I'm sure you remember this. So Bronsted acid, means Bronsted acid is a donor, and when we're talking about donations in acids and bases, that's usually the donation of a proton. A proton is the same thing as saying H plus, because all a hydrogen ion is, the only thing left over in the nucleus is just simply a proton. Don't forget H plus is the same thing as saying hydronium, it's just a simplified version of it. Alright, and then the opposite of that is if it's an acceptor for proton. This one makes no sense, but BBA, Bronsted bases are acceptors. Lewis acids and Lewis bases, we don't talk about these as often, but you definitely need to know these definitions because I'm pretty sure you'll see this definition on the AP exam in some form of multiple choice. Acids and bases are different here because we're not talking about proton transfer, we're talking about electron pairs. So lone pairs of electrons. And the rule is have a pair will share. Okay, so that's kind of like the way you talk about the base here. The Lewis base is going to have a pair of electrons and it's going to share. So the way I remember this one is acid is an electron acceptor here. So acid A, acceptor A. Alright, so that's it for those. Next up is a couple more terminology things that we'll talk about with Bronsted acid bases, or Bronsted acids and Bronsted bases. The conjugates are just what forms from that acid or from that base. So it's the species remaining, and it's always a product of whatever you have reacting in the reactants into what it's turned to in the product side. And like for example, you can have ammonia reacting with water. In this example, ammonia is going to serve as a base because water is going to protonate it. It's going to give it a proton. So that's going to form NH4 and OH minus. So ammonia acts as a Arrhenius base and a Bronsted-Lowry base. So it's accepting the H plus. So ammonia here is a base, but what you do is you travel over to the product side and see what it became. So the definition of a Bronsted base is the species remaining after the acid has donated a proton. So this is our conjugate acid, while this one, the acid, yields our conjugate base. So you have to just make sure you're talking about a base yields a conjugate acid and an acid yields a conjugate base. They're opposites. The stuff in red right here is important. You need to memorize this. Weak acids have strong conjugate bases. That's because when you're talking about strong, it means that it wants to regain a proton or to get rid of a proton. It just depends on which version we're talking about. So weak acids yield things that want to go back to the weak acid phase or the weak acid state. So acetic acid, for example, it yields H plus and C2H3O2 minus. So it's going to yield a weak conjugate base. Same thing down here for acids, conjugate acids. I showed you the example up there. But strong bases make weak conjugate acids. So strong stuff makes weaker conjugates. Weak stuff makes stronger conjugates. Here's an example of a conjugate acid-base pair. Here's our acetic acid reacting with water to make the acetate ion and the hydronium ion. So in this case, water, or the acid is here, the base is water. How do I know that? When I look at the acetic acid form here and what it is in the products, I notice it's donated in H+. Bad acids are donors. So this is the acid, this is the base, and this is going to be the conjugate base, and this is going to be the conjugate acid. The reason that this should make sense is because if you traveled in the reverse reaction, going to the left, who's going to serve as the acid here? That's going to be the hydronium, because the hydronium is going to redonate its H plus to the acetate ion. Alright, so I would like for you to stop, pause for a minute, see if you can fill out the chart of the conjugate acids and the conjugate bases for each of these. Alright, if you pause and you're back up here with me, you got the acid. It's going to donate its only H to make SO4 2 minus, because whenever the H donates, it's going to also take away with it a plus charge, which causes this little minus right here to go down one more charge. HCl reverts to Cl minus. H2O reverts to OH minus. Now let's talk about these in the basic term. Base is the one that's going to gain a proton. So HSO4 1 minus, when it gains a proton, it becomes H2SO4. Notice that this minus charge gets neutralized by the H plus that's being added to it, which allows for it to be neutral in the end. S2 minus, when you add an H plus to that, makes HS1 minus. Only one plus is added to this 2 minus charge, which causes it to go up one charge. And then lastly, we've got ammonia. As you add an H plus, it forms ammonium cation. Okay, so notice that we have one example here where you have an acid and a base, but it's the same compound or same ion. So substances that can act either as an acid or act as a base, meaning gain a proton or donate a proton, is called amphoteric. So another example of that is water, and that is coming up here on the next slide. So you can see that water here, water can react with itself to form hydronium and hydroxide, and the K constant, the equilibrium constant for this, is really, really tiny. You can see it's 1.0 times 10 to the negative 14. That means that does not happen with high favorability. So we do form a tiny amount of those ions, but not significant enough for us to really have to focus on too much. But one thing to notice is that they occur in equal moles. So whatever you get for hydronium, you're going to get the same amount of hydroxide. That's why water is neutral, because you have equal amounts of both the acidic portion and the basic portion. So water can be acidic or basic, or act as a base or an acid. Whenever you talk about your constant K, you have to remember from equilibrium, you learned just a little bit ago, that you take the products over the reactants. Well, both of these reactants are liquid here, so you ignore them and you got both of your products. So this should look familiar to you. It's called the ion product constant. Ion product constant for water, and this number is important to you because you use it in your pH calculations. So we're going to do that in just a minute as well. So whenever these two concentrations are equal, you get a pH 7 solution, which is a neutral solution. Whenever the hydronium one is in excess compared to the hydroxide, you get an acidic solution, so pH less than 7. And whenever it's in the hydronium is less than the hydroxide, then you've got a basic solution, so pH is more than 7. Oh, I kind of did that differently, but you understand what I'm saying. Okay, so for this example, looking at the definition previously, when these two are equal, and you have 1.0 times 10 to the negative 7th, that's when it's neutral. So let's look at this example. If the hydroxide concentration is 7.8 times 10 to the negative 6, because is the solution acidic, basic, or neutral, all you need to do is say, okay, this is to the negative 6. That's actually greater than something 10 to the negative 7. So in this case, that means you have more hydroxides than you have hydroniums available in the solution, so it has to be basic. How do you find the concentration of the H plus that I asked for now? You use the ion product constant. So concentration of OH minus times concentration of H plus is equal to 1.00 times 10 to the negative 14th. So if you know the OH, you need to divide by that. 7.8 times 10 to the negative 6, divide by 7.8 times 10 to the negative 6, that's going to give you your H plus concentration. And you can simply look at the exponents and notice that you'll have 1 divided by 7.8, so you have some number, times 10 to the 14, negative 14, negative 14 minus 8 minus 6 gives you 14, negative 14 plus 6, so that's going to give you 10 to the negative 8. And it might be changed whenever you actually do the 1 divided by 7.8, but that's just how you can simply look at math in your head there. Okay, so here's one pH formula that you need to know. You probably already know it. Don't forget that hydronium can also be written as H+. We also have POH, the same way, equals negative log of OH minus. How do you relate pH and POH? pH plus POH equals 14. And we have another one right here. We just did OH minus times H plus equals 1.0 times 10 to the negative 14th. And then what if there's another equation? If you have your OH or H plus concentration, how do you get back to POH or pH? You do concentration of, I'm sorry, if you have pH, take the concentration of H plus, do the antilog of that, which is the same thing as saying 10 to the negative pH, or the concentration of OH minus, how do you get that? You do 10 to the negative POH. So both of those are antilogs. These are your 6 formulas for pH calculations that you need to memorize and know how to do very quickly. And this one little graph right here just shows you the relationship between pH and POH in the concentrations. There are equations. Just reviewed that with you. You also already know that strong acids have 100% dissociation. We learned that way back in Unit 2. And weak acids do not. That's why we have this reversible arrow here, because not all of this weak acid is going to dissolve to the point where it's going to create the same amount of H3O plus ions as it had over here for the concentration of HA. When you have a strong acid, let's say I give you 1.0 molar strong acid, it's going to create the same amount of that acid, the acidic ion or H plus ion. So if I ever give you the concentration or the molarity of strong acid, assume it's exactly the same as that of the acid or the H plus ion. Weak acids, you cannot do that because there is not a 100% dissociation. I might just set up these for you because you guys can do these calculations through previous equations. But like I just said, if you have your acid concentration, you already know your H plus concentration because they will have 100% dissociation because this is a strong acid. So H plus concentration is equal to 0.0025. Then if you have the concentration, you can automatically do the pH. pH equals negative log of the concentration of H plus, which gives me 2.60. I'm going to tell you this now. The sig figs and pHs are weird. You'll notice that this right here has 2 sig figs in it, the concentration does. So the pH also has to have 2 sig figs, but sig figs only count after the decimal. That is why I have 0.60, because the 2 sig figs are occurring after the decimal in pHs. Okay, so POH, how do you get POH? You do 14 minus pH, so that's 14 minus 2.60. That gives you 11.40. Notice I still have 2 sig figs here. Lastly, to get to the OH concentration, you do 10 to the negative POH. We just calculated that, so 10 to the negative 11.4 gives you 3.89 times 10 to the negative 12 molar. All of these values should make sense. We have a strong acid, so our pH should be acidic. 2.60 is acidic. We have a strong acid, so we should have more H pluses than our OH minuses. That's also true. So sometimes kind of go back and make sure that your calculations make sense to you. The second one is a similar equation. I'm just going to tell you the one difference here. Calcium hydroxide has 2 servings of OH minuses when it dissolves. So it dissolves to Ca2 plus and 2 OH minus. So in this example, whatever you have for your calcium hydroxide molarity, you need to double that to get the OH concentration. So it's not exactly the same. Now, I didn't tell you should do this in acids. You never should, because only the first protonation of an acid is significant. And bases, and our strong bases, we will always do that. So you've only got 3 strong bases that have a 2 for the hydroxide, so it won't happen too often. The rest of these, this is your concentration. I'm sorry, I already multiplied this by 2. This is your concentration of OH minus. You can do the rest of it. All right, one last thing to show you is if we wanted to determine the pH of something when it's mixed with some other substance, so mixed with a new strong, mixed with another acid, like here, so we have a strong acid mixed with a weak acid, a strong base mixed with a weak base, a strong acid mixed with a strong acid, a strong base mixed with a strong base, or a strong acid mixed with a strong base. We'll just do this other stuff when we get to buffers, so don't fret too much, but I do want to show you how to set up some of these. So if you have a strong acid and a weak acid, the strong acid gives 100% H pluses as to whatever the concentration of the strong acid is. So take your molarity of your strong acid, take your molarity of your strong acid to be moles per liter. So that'll be moles of H plus from your strong acid over the liters that the entire solution exists in. So now that the strong acid is now that the strong acid is mixed with the weak acid, it's mixed in a larger volume. So you need to account for that larger volume by doing total volume of the strong acid plus the weak acid, because it is going to dilute the concentration some. You do not have to add the moles of H plus from the weak acid because it doesn't significantly give any. So once you get this, you'll use that to calculate pH by doing the negative log of your new diluted H plus concentration. If you have two strong acids, both of these create 100% the same number of H pluses. So you're going to take the moles of H plus from both strong acids, and then you're going to divide by the new total volume to give you the H plus concentration. So in this case, what you'll have to do to get to the moles of H plus, you're going to have to take your molarity given to you, the acid, times the volume to give you moles, and then do that again. Molarity times volume to give you moles. So this is moles of H plus from the first acid, and this is the moles of H plus from the second acid. So just getting the moles of H plus, it's fairly simple. You just have to look at the givens given to you in the problem. Next example is where you have a strong base and a weak base. It's really similar to the first one, where you have a strong acid and a weak acid. So in a strong base and a weak base, you need to take the moles of OH minus from the strong base. How do you get that? You have to do molarity times volume to give you moles. That's the same exact thing. And don't forget, if it's got two OHs, then you need to double that. You need to divide that by the total volume given to you by the strong base plus the weak base volumes. That's going to give you your OH concentration. Once you get that, you'll take that and go to H plus concentration with your ion product constant, 1.00 times 10 to the negative 14, and then you get your pH of the solution. So these are fairly simple if you recognize your strong and weak acids and strong and weak bases. So this one 100% ionizes, this one does not. Strong base and strong base is very similar to strong acid and strong acid. Both of them contribute to the OH concentration. So you're going to take your moles of OH from both strong bases and divide it by your total volume of strong bases, both of them. And that's going to give you your OH concentration, and you'll do the same thing as before here to get to your H plus and then your pH. The last one's a tricky one. This is if you have two different types of solutions, so one acid and one base. If you have an acid and a base, they will react. They will have a neutralization reaction going on. So you have to have an acid plus a base yielding a salt plus water. And you're going to have to figure out who do you have left at the end of this reaction. Do you have acid left over or do you have base left over? So you're going to have to start off with before reaction, during reaction, after reaction. Take the number that you have here and number that you have here of moles of acid, moles of base. In your head, divide by the coefficients and figure out who your LR is. So let's say I have a limiting reagent of acid. So minus that number of acid, minus that number of acid here in the correct mole ratio, you're going to have 0 left of the acid, you'll have some amount left over of the base, and you'll have some left of the salt and water. I'm not going to worry about that side right now. So if you have base left over at the end of the reaction, you'll have moles of OH indicated in the after reaction portion. You can't go straight to pH. You have to first divide by the total volume of the solution. That's going to give you your OH concentration, and then you can go to pH after you go through the PO. Either go to POH first and then go to pH, or go to OH minus concentration and then go to pH. Okay, that's pretty much every type of mixture problem. You're going to have to do some of these with me, some of these without me. So try looking at these at the methods used, and please go back and memorize your 6 strong acids and 6 strong bases. All right, and we will do the rest of these tomorrow. Thank you very much.